Hello, welcome to the presentation of my results of the constant velocity lab. First of all, I want to describe the build-up of my experiment. It consists of a table and a massive metal ball which will be pushed once by hand so it moves from one end of the table to the other with approximately a constant velocity. The mass of the ball is 0.717 kilograms and the length of the table is 1.8 meters. Now let's look what happens. So the ball moved as expected. Now, to further analyze this movement, the tool tracker will be used next. First, one has to specify the frames where the ball moves with constant velocity, which is just after the ball was pushed and before it falls from the table. In this case, these are the frames 43 to 103, which equal a time of 2.4 seconds. Then, one has to make sure that the lengths in tracker are correct by specifying the length of the table with a calibration stick and some markers on the table that are at the start and the end position of the movement of the ball. Finally, the origin of the coordinate system is set to the center of the ball of the first regarded frame with positive x to the right and positive y upwards. Now, by specifying the center of the ball in each frame, the exact data of the movement can be obtained. Next, a model has to be created that predicts the movement of the ball. The results will then be compared with the data of the experiment. For this model, Newton's second law is used. From this, it follows that the new velocity of the ball after some time delta t depends on the ratio of the current net force on the ball and its mass plus its current velocity. The new position can then be obtained using this velocity. Then, again, the new velocity can be calculated, and so on. In general, it's important that the time steps are small, so the net force and the velocity don't change much. But for this model, a constant velocity is assumed, so the net force must be zero anyway, and it does not matter in this case. The model also requires some initial values from the experiment data, like the start time, initial position, initial velocity, and the length of the experiment. The initial velocity can be calculated with the first two ball positions and the time that elapsed between them. Now this model is implemented with Python. In the code, first the mass of the ball and the other initial values are defined, and the time step length is set to 0.01 seconds. Then, the new velocity of the ball and the new ball position are calculated. The time is increased, and the results are written into a file. These steps are executed inside a while loop for the length of the experiment. Notice that the net force is set to 0 to get constant velocity. Now we can execute this program and compare the results with the data from the experiment. To better compare the results, the data of the experiment and the model predictions are plotted into the same graph. In this graph, the x-axis corresponds to the elapsed time and the y-axis corresponds to the x position of the ball. The red line represents the model predictions and the blue dots are observations from the experiment. We can see that the model approximates the reality very good at the beginning, until 0.5 seconds. Then the differences are getting bigger. At the end of the experiment, there is a gap between the prediction and observation of about 20 centimeters. This is because the assumption of the constant velocity is not completely right for a ball moving on a surface. There are always some forces through friction or even air resistance opposite to the ball's velocity, which cause the velocity to decrease. The error through this is very small in the beginning, as one can see in the graph, because the predicted velocity and the actual velocity are nearly the same. But the more time elapses, the bigger this difference gets, which leads to a bigger error each time step. These errors then accumulate with advancing time, which lead to growing differences between prediction and observation, as again can be seen in the graph. So in order to get a better prediction, one also has to consider forces through friction or even air resistance in the model.